largely the same as we did here. Since we know the y position, which was minus 5 meters, notice we put negative because it falls below the horizontal level. Minus 5 meters was y. That's the y component of our initial velocity, and then that's t that we're going to solve for. We get a quadratic equation like this. I have to solve that quadratic equation using the quadratic formula, which you used in this problem. I think you maybe had one homework problem where you had to use it, but I'll give you the formula if you need it for your exam, but just be aware that you might need to use it for the exam. And then we solve for the time, being careful with our signs. You can be a little tricky with our signs, noticing here that b and c are both negative, and then we have some negatives in here, so our negatives sometimes cancel out. We get 2 times, one of which is positive, one of which is negative. The negative just doesn't make any sense, so we drop it completely. And then the positive is our time when it reaches this point, which is 5 meters below. Now the second part of this question asks, what is the velocity at this point? Since we know the time, this is fairly straightforward to do. We just calculate both the x and the y components of the velocity. So for part 2, or b, we want to know what is Vy at t equal 2.4, and then also what is Vx at t equal 2.4. Once we find Vx and Vy, we can do the square root of Vx squared plus Vy squared, and that'll give us our answer, which is the magnitude of the speed, the magnitude of the velocity, or the speed. Remember, we have, when we get to that point, at the end of the trajectory, we have an x component of the velocity, Vx, and we have a y component of the velocity. The x component remains the same all throughout the trajectory because the acceleration in the x direction, gosh, what is it? Is it net minus 10? It's 0, right? The acceleration in the x direction is always 0 for these. There are no forces acting on it, so it doesn't accelerate. We'll get into forces in the next chapter. We can also, let's see, I don't think I've calculated Vx yet, but Vx is equal to V0 times cosine theta. V0 was given 25 cosine of 23.57, and that gives me a Vx of 23 meters per second. Remember, that doesn't change. However, Vy does change because we have an acceleration. So my Vy is going to equal to V0y plus Ay times t. Hopefully this is going to come out negative, because we want it to come out negative. And it should also come out to be greater than the magnitude of V0. You follow what I'm saying? Let me draw you a picture before we calculate it. Here, V0y is in that direction. And then it gets smaller, and then it goes to 0, and then it gets bigger in the negative direction. And right here, it's going to be the same magnitude as it was over here, but in the negative direction. So it's going to increase even more when it drops down a little lower, because it has extra time to accelerate in the y direction. So when I calculate this Vy, I should find, 1, that it's negative, and then 2, that it has a magnitude that is bigger than V0y, which we found to be 10 meters per second. So that'll give us a little checkpoint just to make sure that our answer makes sense. But it should do both those things. So I already know V0y, it's equal to 10 minus the plus negative 10 meters per second squared. That's my acceleration times 2.4. That's the time that I found. That's 10 minus 24, or negative 14 meters per second. So that means that I found that it is bigger than this in magnitude, and it is negative. So here I can do the square root of 14, or negative 14 squared, plus 23 squared, and then that gives us 27 meters per second. Okay? Now, we also want to know the angle. That is the magnitude of our velocity. We also want to know the angle for the velocity. Remember, when we have vectors, I have my Vx here, I have my Vy here. This is the vector that I'm looking for. I want to know what is this angle. So how am I going to find that angle for this final velocity? Use one of my trig functions. I can use any one of my trig functions actually, because I know all three sides of this triangle. But if I know Vx and Vy, that's what I want to know this angle. I use the tangent because this is my opposite, this is my adjacent. Tangent of Vy over Vx is equal to, our inverse tangent of Vy over Vx is equal to our theta. And that turns out to be 31 degrees. And then we want to add a qualifier below the plus x axis. Good test question, that one. Any one of these three, actually any one of these three or any one of the homework problems are going to be good test questions. You'll have, well, I haven't fully decided what the test is going to cover. It's probably not going to cover all of Chapter 4, but we're going to start on Chapter 4. I'm thinking that we'll save some of the more difficult stuff on Chapter 4 for the next test, and then we'll just sort of have the more simple one-dimensional problems for this test. And once we get into 2D problems, those are kind of involved. But you will definitely have projectile motion, and you might even have 2 free response problems on the projectile motion. Okay? Be able to solve systems of equations, like we've done. Be able to solve just our basic projectile motion problem, where we're starting at one point, beginning and ending at the same horizontal position. Be able to use the quadratic like we did here. Be able to solve problems here where it doesn't end at the same starting position. Okay. Did we do all of the clicker questions for this? We did finish all those. Those are good places for you to practice for the multiple choice, but also go through your notes as well. All right. Any questions right now or issues with projectile motion? You've done all the homework and you feel comfortable with it? Have you some of these? I know some of you have, but if you haven't, please do that this week. If you have questions, I'm around to help you. Okay? It's a tough chapter, projectile motion, so make sure that you're allowing enough time for it. Questions? Issues? I can move on to chapter 4, is that okay? Practice that homework. It'll help you with chapter 3. It'll help you prepare for the exam. I did notice actually let me give you all this one thing. I did notice I was looking back at some of the old exams, and I noticed that a lot of the problems there, I gave you your vectors in, let me show you. If you look back at the old exams, that's the wrong class. The projectile motion problems, let's look at Law 14. I think this is a good example. No, I guess that's not it. That is a good example. Law 14. It's a good example. What will be on the test? This one, number 8. You zoom in a little bit so y'all can see. This is more of an example of what you won't see on the exam. We haven't spent a whole lot of time on these type of problems where we deal with the vector notation. So, but you see these type of problems on the exams, on some of the older exams, but you're going to have more typical word problems like what we have in the homework and the supplemental problems. But if you see these in the homework, you should be able to work them if you think about them, but don't so them. You won't see this form of problem on the exams. Is that clear? All right. Because we haven't spent much time on it, but we'll be spending time on similar things in the future. Okay, let's move on to Chapter 4. Chapter 4 is on the laws of motion, on Newton's laws of motion. Newton came up with his 3 laws of motion. If you had physics, in fact, if you went to school at all, you've seen Newton's laws, even if you didn't take physics, right? In like 2nd grade, they covered it. Is that true? 2nd grade, Newton's laws? No, they do now in 2nd grade. But Newton's laws of motion, He's pretty famous for them, but you know what else he should be famous for? We talked about this. Calculus. He invented calculus. But he did come up with the laws of motion, largely, well, he sort of did this in parallel with calculus, tangent to it. But he really changed the way that we think about motion, because prior to Isaac Newton, we sort of subscribed, or we did subscribe to this Aristotelian view, Aristotle, who predated Newton by, I don't know how long, hundreds of years? I'm not sure. But had a very different view of motion than Newton proposed. And so we'll look at how he viewed motion and how we view motion, or at least how we should view motion today, the motion of objects. We'll get into force diagrams in this chapter. That'll be the big brunt of it. As I said, likely we won't have all of this on the upcoming exam, which is coming up soon, y'all. Like we have fall break, and then we come back, and we have Monday, and then if I'm not mistaken, it's that Wednesday. Am I correct? Yeah, so it is coming up soon. We'll have all of Chapter 3 and part of Chapter 4. Did we cover all of Chapter 2 on the previous exam? We did. So we'll have all of Chapter 3. That's vectors, projectile motion, and then the one-dimensional problems, likely, I'll give y'all more information later, the 1D problems for the force. That'll leave out the 2D for the later exam. Okay, so there are two types of forces. Our force is just a push or a pull on an object. There are two types of forces that we'll be dealing with, and those are contact forces and field forces. We're probably more familiar with contact forces. It's just any time that you apply a force to something that requires contact, so it requires touching. You ever been in a fight before? Who's been in a fight? Like a fist fight. Just one, two people, three people. It's like all the guys. Women, y'all never been in a fist fight before? No. I was in a fist fight with Nelson Zamora in junior high, I guess, middle school, like 8th grade. It was very typical. It was like, let's meet up behind the school after class, and we'll go there. We had a fist fight. I don't even remember what we were fighting about. But then it's like after that, we were good buds. And Nelson Zamora. I'm not even sure who won. I think that we were both pretty beaten up from the whole thing. But anyway, those are contact forces. Anytime that you have contact with a surface and exert a force on something. Those are contact forces. They require contact between two objects. Why is it that guys fight and women don't? Women fight in a different way, is that right? Yeah. Okay, so field forces is the force residing to an object or the force due to an object residing in some force field. Listen, we're going to deal with fields either the end of this semester or the beginning of the next semester until you're just sick of them. But a field is really just a way of measuring a force. You don't need to worry too much about it right now because we'll talk about the mathematical tools that we use to deal with them. But a field, we know some examples of fields like the electric field and the gravitational field. But for now, all you really need to know is that field forces don't require contact. So I'm going to just put that in parentheses here, don't require contact. So like right now, between you and the student next to you, there's a force between you. It's an attractive force, actually. And then also within you, there are other field forces that work between the charges in your body. So we have 4 different types of field forces. You just need to be familiar with them, especially the first two. Is the gravitational force. This is between two masses, the force between two masses. And then also the electric force. This is between two charges, which we'll deal with next semester. Gravitational force we'll deal with in this chapter, and then more in detail later in the semester. And then there are two other forces. You really just need to know them in name only. Know that they exist, so they give you a total of 4 field forces in nature. And the first is the strong nuclear force. Have you ever thought about why a nucleus stays together? That'll blow your mind. Right? Why does a nucleus stay together? Because you know that if you bring two charges together that are like charges, two positive charges or two negative charges, they're going to do what? They're going to repel one another. So what holds the nucleus together? Because actually, you know, those protons are really, really close together. They're very close together. So the electric force for those protons is immense. And so what holds them together? Dun, dun, dun. It's the strong nuclear force. So the strong nuclear force, it binds our nucleus together. And that's really the only other place that we see it. It binds a nucleus together. And then there's a fourth. Like I said, you just need to know it in name, and that is the weak nuclear force. That is, it occurs in radioactive decay processes. All right, know these mainly, know these in name. All right, just know that they exist. You could have a multiple choice question about these, but you won't see it on the free response. But a multiple choice just, you know, which of these is a field force? And it would list several forces, and you would have to pick out those that are field forces. All right, let's look at Newton's first law. Newton's first law, actually before we do that, let's watch a video. This is Veritasium. And what he does here is he describes the laws of motion. Listen, we all have ideas about how things move. You have an idea about how things move, and usually those ideas are incorrect. It's because Aristotle had ideas about how things move, and he got those ideas by observing the world. And you likewise have seen things occur, and you create these ideas about how things move. But it turns out, and this is why Newton was so groundbreaking and why he was such a genius today and in his time too, that those ways that we observe the world are incorrect. And they're, or maybe not incorrect, but just not completely informed, that we're not considering certain things. So in this video, he talks about the common ways that we view the laws of motion, and probably the way that you view the laws of motion, and sort of lays out Newton's 3 laws in an incorrect fashion. Okay? Let's watch it, and then I'll give you the actual laws. Well, no, actually, let me give you Newton's first law, and then we'll watch it. Okay? All right, so Newton's first law is an object moves with constant velocity unless acted upon by a force. And that constant velocity also can mean v equals 0 or v greater than 0. So either stationary, that would be constant velocity, or constantly moving at a certain velocity. So it moves with constant velocity unless acted upon by a force. We call this the law of inertia. Let me see. I'm going to go down for just a second. I'll be right back. Yeah. We call this the law of inertia. Inertia is the tendency of an object to continue in its original state of motion. This is really just a restating of the first law. So the tendency of an object to continue in its original state of motion. And inertia we measure with mass. So mass, which we measure in kilograms, is a measure of inertia. What's going to be harder to move? The desk, which weighs, I don't know, 50 pounds, or the chair, which weighs 10 pounds? Which is harder to move? The desk or the chair? The desk. Now, part of it's due to the frictional forces that are at work. But if you had the desk and the chair out in space where there were no forces acting upon them, the desk would still be harder to move. It would still have a greater tendency to continue in its original state of motion, just because it has a bigger mass. Right? So this is a direct measure of our mass, and it's also just a restating of Newton's first law. Let's also define a net force. A net force is just the sum, the vector sum, of all the forces. We're going to be doing this a lot, but let's say that I have an object, I have a force, we'll call it F1. I have a force in this direction, we'll call it F2. Let's say that F1 is equal to 20 newtons, F2 is equal to 10 newtons. A newton is a measure of force. I'll define that in just a bit. But for now, the vector sum of this, I can write in a couple different ways. I can say the sum of all the forces, that's the vector sum, or I can say the net force. That's implied that it means the vector sum of all the forces. And in this case, it's going to be F1 minus F20, because we're doing minus F2, because we're doing a vector sum. One vector is in the positive direction, one vector is in the negative direction. And so the vector sum of these would be what? 10 newtons. It would be 20 minus 10, which is equal to 10 newtons. We're going to get into as well when we have multiple forces, like if I have an object that has multiple forces like this, then to find the net force will be to take all the forces that are acting that in the x and the y directions. So we'll get into that later, but likely not until the next exam. Let's watch this video. Alright, so he said that an object will, with no unbalanced forces on it, will do what? It'll eventually come to rest. And that's what we observe, right? If I do this, then it comes to rest. And in fact, everything that we see, most things that we see, come to rest. And this was Aristotle's view. He said that things have this natural state, that they exist in this natural state of being at rest. And it was almost a metaphysical idea. It wasn't even really a scientific idea. He thought that it was violent in some way to take something and put it into motion. In one of his writings, he talks about shooting an arrow up into the sky, and he talks about how you're violently ripping it from its state and putting it up into the heavens or whatever. So it was sort of a metaphysical thing, not so much a physical thing. Newton came along and said that no, none of us have a natural state of motion. Our natural state of motion, or our state of motion just is what it is, and it's not going to change unless you have a force that's applied to it. Okay? So that's the first law, is that an object is going to stay in its state of motion unless acted upon by a force. Let's try this quick test. That first law, by the way, is called the Law of Inertia. Let me pull up my clicker base. Okay, true or false? If an object moves with constant speed, the net force equals 0. So if an object moves with constant speed, the net force equals 0. Is that a true statement, or is that a false statement? A if it's true, B if it's false. All right, ask your neighbor, think about what this statement is saying, and think about how it jives with Newton's first law. This says if an object is moving with constant speed, then the net force on that object is equal to 0. There's one Newtonian way to think about this, and then there's an Aristotelian way to think about it. I'm going to stop at 115. Okay, so most of you put false, that is a false statement. So let's go back to what Newton's first law says. I hate true-false questions, don't y'all? Yeah, they're kind of confusing, but they help you to think about things. So, an object will move with constant velocity unless it's acted upon by a force. So, if I have a force that's acting upon it, then it's going to move with an increasing velocity or a decreasing velocity. So let's go back to our statement. If an object moves with constant speed, the net force is equal to 0. What if the net force was not 0? Would it move with constant speed? Yes or no? No. So in this case, if an object moves with constant speed, the net force is 0. That is a true or a false statement? What do you think? It is a true statement. But if an object moves with constant speed, i.e. it's not accelerating, then the net force will equal 0. That comes out of Newton's first law, but it also comes out of the second law. Let's look at the second law. The second law is called the Law of Acceleration. Newton didn't really write it like this. I'll show you how he wrote it, but let's just write it how we typically write it now. And that is that the acceleration is dependent upon a couple of things. The acceleration is directly proportional to the force. So if I give a force a push or a pull, that's going to cause it to accelerate. If I give a bigger push or pull, that's going to cause it to accelerate more. The acceleration is inversely proportional to the mass. So if the mass is bigger, I'm going to accelerate less, given the same force. And so we can put these together, and I get A equals F over M, or as we more commonly write, F equals MA. Remember, the incorrect law of motion was he said that if you give a force, then it gives you a constant, not acceleration, but velocity. And that's typically the way that we think about things. You know, normally the way that we think about things is in a world without friction. Because in Aristotle's time, they didn't really know about friction, what it was or how it operated. And in a similar way here, in a world without friction, in the first law, in a world without friction, then things would move constantly without ever stopping, because they wouldn't be stopped by the frictional forces. Now in this case, if I apply a force, I get a constant acceleration. You don't need to know this, but if you know what momentum is, don't even write this down unless it's familiar to you. Momentum, which we'll get to in a couple of chapters, chapter 6. Again, don't write this down unless you know what I'm talking about. But momentum is equal to mass times velocity. And what Newton really wrote in the first law was that the force was equal to the derivative of the momentum. And since momentum is mass times velocity, this was mass times dv over dt, which is our mass times acceleration. We'll come back to this in chapter 6, but this is really what Newton said. He said that the momentum of an object is mass times velocity, and the force is equal to a change in this quantity. So if you know what momentum is, this might help you to understand this a little better. If you don't sweat it. We'll get to it in chapter 6. But our force is equal to the mass times acceleration. Let's see. Let's work this problem. I don't have an overhead, so I'll just tell you what the problem is. Oh, shoot, I don't have it here. I think I can remember it. This problem, which I've taken from an MCAT prep thing. Any pre-meds? How many pre-meds we have in here? Okay, a few of you. There can be quite a bit of Newton's law stuff. You know, the MCAT is sort of different year to year, and sometimes there's a lot of physics, and sometimes there's hardly any physics at all. But you will see, if there is physics, you're likely to see some Newton's laws problems dealing with force diagrams and what have you. This one's pretty simple, but let's say that I have a rocket
of 1,000 kilograms, and it has a propulsive force of 20,000 newtons, 20 kilonewtons, and air resistance of, let's just say, 1,000 newtons. What is the speed of this object after 8 seconds? Of the rocket. Okay, so this is sort of like our kinematics problems that we've been dealing with. In fact, with Chapter 4, you'll still see some kinematics. They won't be quite as complicated as we saw in Chapter 2 and 3, but you'll still see some simple problems, kind of like this. Where here, first, I need to find out what the acceleration is. Actually, my first step is to figure out what is my net force. Whenever I'm dealing with these problems, I always like to draw a picture first. So I'll draw my rocket. There's my rocket. It has a propulsive force of 20,000 newtons. So I'll draw that as a force here, 20,000 newtons. And then it has a resistive force, that is, it's opposing the direction of the motion, air resistance, of 1,000 newtons. And so my first step is just to find the net force. The net force is the vector sum. So that's going to be, well, what is going to be my net force in this case? Is it going to be 21,000 or what? It'll be 19,000. It'll be 20,000, which is in the positive direction, minus 1,000. So 20,000 newtons minus 1,000 newtons, and that's equal to 19,000 newtons. Next, I want to find my acceleration. So I know that A is equal to the net force over the mass. That's from Newton's second law. The net force here is 19,000. My mass is 1,000. So that gives me an acceleration of 19 meters per second squared. And then the final step is to do my kinematics. And so I want to know its final velocity or its final speed. I know the time. I know the acceleration. I have my kinematics equations. So I'd say V equals V naught plus AT. We'll assume that V naught is 0. That's 19 times 8. It's at 80 plus 72, 150. 150 meters per second. So with these Newton's laws problems, you could see some simple, I would say simple, but one-step kinematics problems thrown in there towards the end. Where first you have to go through the Newton's laws, through the Newton's second law, to find the acceleration, and then calculate the velocity of the position after a certain amount of time. This is the basic process that you'll follow with all these problems. You'll see later that we'll get some that are quite a bit more complicated, just mathematically. But it's going to be the same process every time. Draw a picture. I like to draw a picture. And I recommend that you do too initially. It'll help you to think about it. Figure out what is the net force. In this case, it's just in one dimension. So it's a lot simpler than if it were in 2 dimensions. And we'll get into some 2D problems. Calculate the acceleration, and then whatever it is we're asking about the object. Find that. Okay? All right, let's do some let's try this question. This figure shows an elevator that is accelerating downward at 2 meters per second squared. A 10 kilogram mass hangs by a rope inside the elevator. What is the tension in the rope? And something I haven't told you, I'm sorry, I meant to tell you earlier. But when we're figuring out the weight, the gravitational force, that is called the weight, that force weight is equal to the mass of the object times the acceleration due to gravity. So in this case, I have 10 kilograms. What is going to be the weight of this object? it's going to be 100 newtons. So I'll try and draw that here. I have a force, weight, equal to 100 newtons. I'm going to outline on the side here the steps that you'll go through, and then I'll let you go through the steps on your own. But let me show you the steps here. The first is draw all the forces. All right, so here I've drawn one force for you. Do y'all know how many other forces there are acting on this object right here? 1, 2, 3. How many other forces are there? There's only one other force. There's only one other force acting on this object. You want to draw all the forces. Then you want to find the net force. Or rather, you want to write an equation for the net force. You want to apply Newton's second law. That is that F is equal to M times A. And then finally solve for whatever it is that you're solving for. So you want to draw all the forces. I drew one force here for you. Determine an equation for the net force and apply Newton's second law, F equals ma, and then solve for whatever it is that you're solving for. Alright, so there's one other force. You need to figure out what that force is. Right, the tension and the strain. And then you'll want to figure out what your net force is, and then set that net force equal to our mass times acceleration. Be careful with your signs on things when you're dealing with vectors. If they're down, they're negative. If they're up, they're positive. I got new shoes. My shoes are very squeaky. You like my new shoes? They're just like my old shoes. I have the same shoes. I just buy them, and I keep them in my closet. But like when they're on sale, I pick them up. Do you like them, Steve? Very comfortable. Only about 7 of you have the right answer right now. And about 7 of you have the wrong answer. Yeah. Oh, so the 100 newtons is the weight of the object. The object is 10 kilograms. And the weight of the object, I just told you this, you didn't know it beforehand. But the weight of the object is the mass times the acceleration due to gravity. So since it's 10 kilograms times 10 meters per second squared, the weight of the object is 10 newtons. We're going to use that a lot, so you'll get it. All right, we'll stop in about 10 or 15 seconds. I see that nobody's put D. That's good. If they put D, that means the weight is 100 newtons. That means that whatever the weight is also the tension. But you seem to understand that this acceleration has something to do with the problem. That because the elevator is accelerating, then that's going to change the tension that I have in the rope. And you're correct. I want you to think about, is that tension going to increase or decrease from, if it was not accelerating, the tension would be 100 newtons. That if I was just sitting here holding this 100 newton block, I'd have 100 newtons down and a tension of 100 newtons up. So think about, would the tension increase or decrease since this elevator is accelerating downward? Because if it's going to increase, the tension would be 120. That's the only one that's more than 100. If it's going to decrease, it'll either be 20 or 80. All right, I'm going to stop here at 550. So just guess if you're not sure. 550. What is that? C? C is right. Good. All right. So what we do here is we figure out what is our net force. Well, first draw all our forces. We have our tension, which is pointed upward. The net force in the y direction is going to be the tension minus the weight. And in this case, applying Newton's second law, the tension minus the weight will equal to the mass times the acceleration. In this case, it's in the y direction. And so our tension, which is really what we want to know, now we're going to solve, the tension will equal to the weight plus the mass times the acceleration. The weight, as we've already said, is 100 newtons. The mass is 10 kilograms. The m that goes here is whatever object is moving. So since our object is 10 kilograms, then that's the mass that we use. And then our acceleration is 2 meters per second squared, right? Is that right? Is it right? It's negative, right. So that's going to be negative because the acceleration is downward. Now, it doesn't tell you that it's negative, but it shows you that it's accelerating downward. So that's going to be 100 minus 20, which is 80 newtons. Let's do a few more problems. We'll do some of our quicker problems. Okay, this is regarding Newton's first law. A book is lying at rest on a table. The book will remain there at rest because which of these? Why does it remain at rest? Read them carefully, each of the options. Why does it remain at rest? All right, I'll stop at, I don't know, 55? 55? Okay, D is right. So it's not that there's a net force, it's not A. If there's a net force, the object will accelerate. It doesn't matter what the mass is. If there is a net force, the object will accelerate. Now, the amount of acceleration is given by the mass, so I know from the second law, F equals m times A. If there's a net force, I will have an acceleration. Now, if the mass is really big, I'm going to have a small acceleration, but nonetheless, I'll have an acceleration. The answer is there is no net force. That's the only way for there to be no acceleration. And here, it's at rest. It's not moving at all. And so we can assume then that the acceleration is 0. Now, I know what you're thinking is that we had a situation in the previous chapter where things were not moving, but their acceleration was non-zero. Do y'all recall? We said that when we throw an object up in the air, that at the top it's not moving for just an instant, but its acceleration is still -10. This is a different situation because the object is just sitting there in time and space. It's not moving at all. And in this case, the acceleration is 0. Okay? So if the acceleration is 0, there has to be no net force. A hockey puck slides on ice at constant velocity. What is the net force acting on the puck? Remember, go back to Newton's first law, folks, that if I have something moving at constant velocity, or even Newton's second law, what does that tell me about the acceleration if it's moving at constant velocity? And then take that, what it tells you about the acceleration, and ask, what does that tell me about the force? All right, I'm going to stop at 1 minute. 1 minute. Okay, E is right. If it's moving at constant velocity, that means it has no net force acting upon it. Now, at some point, a force had to act upon it to accelerate it from rest up to some constant velocity. Or maybe it's been moving at constant velocity for all of its existence. But at some point, a force probably acted upon it. But at this moment, this hockey puck has no net force acting upon it. Are there forces acting on the hockey puck? There are forces acting on it. But the sum of all those forces is going to equal 0. Remember, the net force isn't just one single force, but it's the sum of all the forces. You put your book on the bus seat next to you. When the bus stops, suddenly the book slides forward off the seat. Why is that? Riding along in the bus or in your car or whatever, all of a sudden it stops, your book slides off the seat and onto the floorboard. Why does it do that? All right, we'll stop at 40. Y'all are very Aristotelian this morning, not Newtonian this morning. 45, we'll stop. Okay, a net force acted upon it. Gosh, what was the force that acted upon the book? Did somebody push it off of the seat? Did you ram it off with your hand? No, there was no force that acted upon it. In fact, that was the reason that it slid off the seat, because no force acted upon it. So the answer here is not A, but it's B. Again, you think you know the answers to these, because Newton's laws, they seem very simple, but when you're posed with questions like this, you're not really applying them correctly in your mind. And that's okay, you'll get the hang of it. But here, no net force acted upon it, because the object is moving at a constant velocity on the bus, and then the bus stops, but the book just keeps on moving. It needs a force to act upon it to keep it on the seat, to make it stop moving as well. All right? If it was to stop, what would be the force that would keep it on the seat? A frictional force. Like if it's sticky enough between the seat and the book, or maybe you'll put your hand down and stop the book. In order for it to stay on the seat, it has to have a force act upon it. Just a couple more. You kick a smooth, flat stone on a frozen pond. The stone slides, slows down, and eventually stops. Then you conclude which of these? I'm free to ask your neighbor. Please do tell your neighbor what you put in fact. And then if we have an argument over it, we can go out and quietly have with field forces. I will stop at 55. Let's see. C. Hey, that's a lot better. So a net force acted on it all along. I think that's worthy of a joke, right? Let's see. How do you get a baby astronaut to sleep? You rock it. Dustin, what's up, man? It's like the fourth punchline that you've given up on me. Don't do that anymore. No, proper joke etiquette is See, when somebody asks you the question, all you say is, I don't know. You don't try to think of a punchline. You don't try to come up with something funny. I'll see you out in the quad afterwards, okay? Okay, the net force acting on all along. Alright, so consider a cart on a horizontal frictionless table. Once the cart has been given a push and released, what will happen to the cart? Well, actually, we'll stop with this one. Let's just stop. The answer is, what is the answer? It's frictionless. It's going to be D. D is the right answer. D is the right answer, and then y'all can go. We'll pick up with these next time. I'll let you know more about the test. I'll think about it between now and Wednesday. Firm.